This is a lecture from Open Tuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
This is the last of the lectures on chapter 11, risk and uncertainty. And I kept it separate because we've two final things to do, which, although they're related, they are rather different from everything else. And they're both, I think, relatively straightforward. Something called standard deviation and something called sensitivity analysis. So first of all, sensitivity analysis. Rather than chat, let me explain with the example. It's exercise 4. Harry is about to consider a new business opportunity. Based on his current estimations, it looks profitable. He's got forecasted sales revenue of 30,000 a year based on 1,000 units sold. His estimated fixed costs to be 15,000 a year, and the variable costs are $10 a unit. Well, it says it looks profitable, but part A says confirm on the basis of the above figures, confirm it is worthwhile. Well, there's nothing new here. This is very basic costing, but let's check. The profitability, the sales revenue, 30,000 a year. The variable costs, it says 1,000 units. I think I said 10 before, but 1,000 units sold. The $10 a unit. So the contribution is 20,000. The fixed costs are 15. And therefore it is indeed profitable. The profit is 5,000. So no problem, that was easy. However, the only problem is, in practice, that all those figures, of course, are just estimates. If the estimates are correct, you know, the revenue really is 30,000, the fixed costs are 15 and so on. If the estimates are correct, this is profitable, should go ahead. But what happens if it turns out any of those estimates are wrong? Obviously, you can never estimate perfectly. Suppose, for instance, the fixed costs turn out to be different than 15. Well, obviously, if the fixed costs are lower, things are even better. Lower fixed costs, more profit. What else if the fixed costs are high? So if there's 16,000, profit's only 4, but okay, it would still be worth going ahead. It's worth going ahead, provided we are making a profit. You know, even if the profit was only $1, then it's worth going ahead. Well, all we mean by sensitivity, as you'll see as I put the numbers on it, we work out what percentage change we could afford in an estimate before it started to become not worthwhile. Now, I said a minute ago, a profit, any profit greater than 0, and it is worthwhile. What percentage change can we afford in fixed costs or in the other figures before the profit fell to 0? Because any bigger change would start loss making. It's not worthwhile. So let's look at part B. It asks for the sensitivity of firstly the selling price. So our selling price, it was based on 1,000 units, so our selling price was $30, therefore the revenue was 30,000. We assume, for the minute, everything else is certain, so variable costs are 10, fixed costs are 15. We say, well, what percentage change in that revenue would result in a profit of 0? Well, think about it. Surely, if the variable stay at 10, fixed costs stay at 15, for the profit to fall to 0, for the profit to fall by 5,000, the revenue would have to fall by 5,000. I don't think I need to write them all down. If revenue falls by 5 to 25, the profit ends up being 0. So we can afford the revenue to fall by up to 5,000. But on its own, of course, 5,000 is that a big fall or a little fall? We do it in percentage terms. We can afford it to fall by 5 on an existing 30, which is a percentage, is 16.67%. So there is the sensitivity. We're not, if it falls by any less than 16%, we'll be profitable. It's still worthwhile. But if it fell by more than 16.67%, more than 5,000, then we're loss-making. It's not worthwhile. Strictly, we should put a sign against it. The revenue, of course, could end up being higher or lower than our estimate. If our revenue's higher, no problem, gets better and better. So we're only worried if the revenue falls. So strictly, the sensitivity is minus 16.67%. All right, well, the others should, I think, be pretty quick. The next one is sales volume. Our costings were done on selling 1,000 units. What's going to happen if sales are different than 1,000? Well, two things will change. Surely if sales were, I don't know, 100 less, the revenue would fall. If there were 10% less, with 10% less revenue. But equally, the variable costs will fall as well. If there's 10% less sales, there's 10% less variable. And so it's the contribution would fall. Again, if there's a 10% fall in the sales volume, 10% fall in contribution, fixed costs stay the same. So we need to look at the contribution. How much can we afford the contribution to fall to get a profit of 0? I hope clearly 5,000. But in percentage terms, it's 5,000 out of an existing 20,000, which I can do in my head is 25%. Again, we're only concerned if the sales volume falls, and so it's minus 25. Well, really, the other two you should be able to do yourself, but I just work, so it takes a second. Total variable costs. Well, if it was only variable costs that were going to change, at the moment they're 10. They'd have to change by 5 for the profit to get to 0. And so the total variable cost, 5,000 on 10,000, is 50%. But here's where the sign again matters. With variable costs, surely, we've only got the problem if they increase. So strictly it's plus 50%. If variable costs fall, then we're even better off. And finally, the fixed costs. Well, again, if you've been happy so far, you should be able to do it almost without thinking. Fixed costs are 15, if that's the only thing we're uncertain of. For the profit to go to 0, fixed costs have to go up by 5 in percentage terms. It's what, 33.33%. But again, the direction for lower profit, we're only worried if fixed costs increase, and so it's plus 33%. So I hope that's very straightforward. He does say comment on the results. Well, the one big comment to be aware of, which I hope is pretty clear, is we only look at one variable at a time. So, you know, I just did fixed costs. They can go up by up to 33%, provided we were assuming all the other flows estimates were certain, the variable costs, they can go up by 50%. But, you know, that was assuming for that bit of calculation that all the other estimates were certain. Whereas in real life, of course, everything can change at once. You know, if variable costs are going up and fixed costs are going up, well, you know, it'll be a smaller percentage of each if they're both going up together. And one can affect the other, you know. A lower selling price might mean we sell more. That's the big limitation of the way we're expected to run a sensitivity analysis. You're only ever looking at one uncertain item at a time. Okay, but I said there were two things in this chapter. That's one. The final one over the page you'll see is standard deviation. Standard deviation. Now, it's actually a measure of spread. If you just look very briefly at the note, halfway down it says, Project A and Project B both have an expected value of 40,000. And so, in ordinary decision-making on expected values, you'd say we're indifferent if they, you know, we pick the highest expected value. If they're both the same, then, you know, we're indifferent, doesn't matter which we pick. But because the expected value was just an average, Project A, it says there's a standard deviation of 2,000. What that means is because it may be, it's on average 40, it may be higher, it may be lower. Project B, a standard deviation of 6,500. Again, average 40, but it may be higher, it may be lower. But standard deviation, as you'll see in the numbers in a minute, is measuring the extent of the spread. How much higher, how much lower. You know, if you were guaranteed it was always be 40,000, there's no spread at all. We have a standard deviation of 0. But the more that the actual results may be higher or lower, the more the spread, the more the standard deviation. So it's a measure of spread. There's a formula there, but I'm not going to talk through the formula. I'll explain the formula as we do the example. It says the following are the likely returns from Project Z. It's either going to give us 10%, 15% or 20% with those probabilities, 0.2, 0.5 and 0.3. So this is best set up as a little table. The return, which for the formula I'm going to use, I'll call X. It could be in dollars, here it's in percentage, doesn't matter. But it's either 10, 15 or 20. The probabilities, which I'll call P for probability, the probabilities are 0.2, 0.5 and 0.3. Well, let's first of all work out the expected return. And of course, for expected return, expected value, we've done this enough times, we multiply the return by the probability and add up. So P times X. 10 times 0.2 is 2, 15 times 0.5 is 7.5, 20 times 0.3 is 0.6. The total, I think, oh heavens above, how embarrassing. 20 times 0.3 is 6. That was just to check who was listening. And so the total, 6, 8, 15.5%. That surely is the expected value of the average return. Oh, the other name for it is the mean. Mean's another word for average. So there's the average. Well, I mentioned before spread. All right, on average you'll get 15.5, but the actual return might be lower, it might be higher. and we want to get a measure of, on average, how much higher, how much lower could it be. And so what we do is we take the difference between the returns and the average, one by one, how much higher, how much lower. Now the symbol we use for the average, it was the average of the x's, we call it x bar, x with a bar over it. So let's look at the differences in each case. X minus x bar. So for each of them, 10 minus 15.5 is minus 5.5. 15 minus 15.5 is minus 0.5. 20 minus 15.5 is plus 4.5. Now what we want is the average spread, the average difference. The only problem is, if you just took an average of those as they stood, you know, multiply by the probabilities and add up, then because you've got minuses and pluses, you'd end up with an average of 0. Try it if you don't believe me. And so what we do effectively to avoid that, we take x minus x bar, we square the differences, and then we'll take a weighted average. We'll multiply by the probability. Because when we square the differences, a minus squared becomes a plus squared becomes, they all become positive. So it's just basically a way of getting rid of the sign. So check me. First one, 5.5 squared times 0.2, because we're taking an average, is plus 6.05. 0.5 squared times 0.5 is 0.125. 4.5 squared times 0.3 is 6.075. Add them up, and what does it come to? 6.05 plus 0.125 plus 6.075. It comes to 12.25. Now, that figure in itself isn't actually a measure of spread. You know, the more it was higher or lower than average, the greater those figures would be, the greater that would be. The only thing is, though, it's the average of the squared returns. You know, the returns are all in percents. I've said before, they could be percents, it could be dollars, it doesn't matter what it is. But because we square, so the differences were in percents or cents or whatever. But because we squared them, that 12.25 is in squared percentages or squared dollars. And so to get back to the same units, the measure we use, which is the standard deviation, because it's squared percents, we now take the square root. It's the square root of 12.25, which is 3.5. And because here the returns were all given in percents, the standard deviation is 1%. Had the returns all been in dollars, the standard deviation would be in dollars as well. So there we are. And if you look back at the formula just stating what I did. What did I do? I took x minus x bar squared and multiplied by the probabilities. We added them up, sigma, to get the average of the squared of the deviations, so 12.25. And then, for the reasons I just explained, we took the square root. So there we are, the standard deviation. Oh, boom. All right, that was easy enough. Oh, sorry, I should never say that, but still. There is one final thing, one final measure to be aware of, It's at the bottom of the previous page. It says coefficient of variation. The point is, we've got a standard deviation of 3.5%. Or again, if you, I'm sorry, I know I've said it 20 times now, but it could be $3.5 if they'd all be in dollars. But is that big or small? You know, if the original figures were sort of 80%, 90%, 100%, 3.5 is very small. But if the original figures were 5%, 6%, 7%, 3.5 is rather big. And so, to give it an order of magnitude, the coefficient of variation why am I bothering trying to write when I can't spell? Coefficient of variation. As you can see at the bottom of the previous page, we take the standard deviation and we divide by the mean. So in my example, the standard deviation was 3.5. The mean, I've lost where I worked it out. What did I get? Was it 15.5? Yes. The mean was 15.5. And so the coefficient of variation, 3.5 divided by 15.5, is 0.226, or 22.6%. Doesn't really matter how you write it, but it gives an order of magnitude. You know, the standard deviation would be 0.5. It's a tiny little spread compared with the 15.5 mean. Okay, so that's it for chapter 11. So we're nearly there.